So we have a problem based on mass transfer. Okay, air at 50 degrees Celsius and 1 atmospheric pressure. It flows over the surface of a water reservoir at an average velocity of 2.3 meter per second. Okay, so first they have talked about the air movement, which is the temperature of the air is 50 degrees Celsius, and it is having a pressure of 1 atmospheric pressure, and it is moving with a velocity 2.3 meter per second over a water reservoir. Okay, the water surface is 0.65 meter long and zero point 0.6 meter wide, and the surface temperature of the water is 30 degrees Celsius, and the relative humidity of the air. Okay, the air above the water surface is 40 percentage. Density of air is given, kinematic viscosity of air is given. You have to determine the amount of water vapor evaporates per hour per square meter of the water surface. Okay, that means we have to find it in the unit kilogram per meter square hour. And the diffusion coefficient is also given. Let's look how to find the amount of water vapor evaporate per hour. So this is a simple drawing of this given condition. A water reservoir, surface is maintained at the 30 degrees Celsius, and air which is flowing above the water surface, it's flowing with the velocity. So that air movement or the region above it is mentioned infinity and the surface is s. So u infinity means actually velocity of air is it means the velocity of air which is 2.3 meter per second. Similarly, T infinity means temperature of the air. Okay, infinity means that's a normal convention using in mass transfer. So infinity simply means the like other region, not the surface. The region above it is usually called as infinity. That's why T infinity. That means temperature of the air. Similarly, velocity of the air. Okay, this all are given condition. Also, relative humidity of the air is also given. So what happens is the evaporation from the surface. This water air is moving, so obviously there will be evaporation from the water on this water reservoir. Okay, we have to find the amount of mass that evaporate. That's our final. That's our aim. Okay. So first, what I have to find is these are all the given conditions. First, need to find the Reynolds number. You have to determine what type of flow it is. That's the very first step in solving this type of problem. We have to determine the kind of flow having, and so for that we have to use the Reynolds number equation. Basically rho v L by mu. Here we are not using v in place of v velocity. Here u infinity. Okay, we need to find the flow means the airflow. Okay, the airflow can be either turbulent or laminar. So the to find whether it is laminar or turbulent, the only way is to determine the Reynolds number. Okay, which is given by the formula rho v L by mu. In the place of u, it's u infinity. This is velocity. Okay, so rho means the density. At least this length along this direction is all given in the question. Density is given. We know the length, dynamic viscosity. We know it. Okay, velocity. We know it. So simply substitute, we get Reynolds number as this much value 85 into 10 raised to 3. So the condition which separates the laminar or turbulent is this value. If the Reynolds number is less than 5 into 10 raised to 5, it is laminar flow. If it's greater than 5 into 10 raised to 5, it is turbulent. And the value we got here is less than 5 into 10 raised to 5. So obviously it is a laminar flow. Okay, now we got it as a laminar flow. Next, diffusion coefficient we have to, uh, I mean, diffusion coefficient is given, that is 0.25 into 10 raised to minus 4 meter square per second. Next number or term we need to find is the Schmidt number, which is given by this formula mu by rho d. Mu is the dynamic viscosity, rho is the density, and dAB is the diffusion coefficient. Okay, so finding that number, before that we need to learn this equation. Okay, this is Sherwood number. So it is given by this formula 0.664 into Reynolds number along the length whole raised to half into SC, that means Schmidt number whole raised to 1 by 3. So now we know the value of Schmidt number. We know the Reynolds number. So uh, we can substitute and find the value. Sherwood number. This SH is Sherwood number. But there is also other formula for Sherwood number, which is given by HM L by D. HM is not H into M, which is H subscript M. HM means mass transfer coefficient. Okay. So this equation is similar to what we learned the heat transfer equation. Like so here HM means the mass transfer coefficient. We are having a mass transfer case, so this Sherwood number is also have another formula. In addition to this formula, we have also have another formula for Sherwood number, which is HML HML by D. HM is the mass transfer coefficient. So we have two equation having left hand side same. So we obviously we can equate the right hand side. So from this equation, we can find the value of mass transfer coefficient HM. Okay, cross multiplying, we get the value of mass transfer coefficient. So that's the very first step we have to know. First of all, find the Reynolds number, determine whether it's laminar or turbulent, and use find the Schmidt number and find Sherwood number. Along with the use of the formula Sherwood number, and use the formula to equate and find the mass transfer coefficient. So now we have the value of HM, mass transfer coefficient. Next step is to determine the partial pressure of the water vapor. The first thing along the water surface, we know this maintained at a temperature of 30 degrees Celsius. So how to find this value? You have to use a steam table. There will be a column of saturated like water temperature. So the corresponding temperature is 30 degrees Celsius, and you will get the corresponding pressure, partial pressure there. Okay, in steam table it may be in unit of bar, but you have to find the unit in kilopascal. So the partial pressure of water vapor along the water surface, I mean at 30 degrees Celsius is this much value. So this can be find out by steam table. So similarly, you need to find the value of saturation pressure at 50 degrees Celsius, that means the air. Okay, so same way you can find the value in the steam table. But here an additional data is given, the relative humidity of the air is given at 40%. So you have to consider that value also in order to find the partial pressure of the water vapor at air at 50 degrees Celsius. So multiplying it with the normal partial pressure with the relative humidity, you will get partial pressure of water vapor at that relative humidity. Okay. Now we have the value of PS1 and PS2. Okay, partial pressure at the water surface and the air. So the next step we have to, I mean, the final stage is to determine the concentration. Okay, mass concentration and of the both the part, I mean, air and surface we have to determine. So it is given by rho V, rho W1, okay, or rho S. I mean, this is surface and this is infinity means that air. Okay, so it's actually derived from the formula PV is equal to nRT, where n is the number of moles, which is mass in gram by molecular mass, and we know that mass by volume is mass concentration. So from that equation, this equation derived. Just have to learn this formula. Okay, if you don't want to know where it came from, you just learn this formula. Rho S or mass concentration is given by PS1 into like molecular weight by, I mean, universal gas constant into temperature. The only difference is the partial pressure, but the air means sorry, the water vapor means we are using the molecular weight of water vapor H2O, that is 18, and the temperature also we consider only the surface. Okay, so from using this equation we get the concentration of two partial pressure region. So final step is to determine the mass flux of the water vapor, right? How to do that? So this is the final equation we'll be using, mass flux of the water vapor evaporator. Okay, this type of evaporation of the water vapor into air, we'll be using this equation. So NWA flux means divided by area, right? It's flow rate by the area. Whenever mass flux means we have to divide the mass flow rate by area, which is given by the formula HM into difference in the concentration, which is rho s minus rho infinity. I mean surface concentration minus atmosphere or the air concentration. So if you find the value, already it's mentioned the question we have to find in kilogram per meter square hour. For the normal equation only give kilogram per meter square second. So we have to multiply it by 3600 because 1 hour is 3600 seconds. So we have seconds. So how to convert hour, we have to divide by 3600 and that 3600 will go to the numerator. That basically means you have to multiply this term by 3600 to get the unit in kilogram per meter square hour. So we may, if you look, we got the answers negative. The mass flux of water evaporate negative. That means here you can see this equation is given in like, you know, this equation is in the form like concentration of surface minus infinity. That means surface concentration higher and like the atmosphere or air is less. And by taking that way, we got the answer negative, right? That means it is actually went in the opposite direction. That means atmosphere concentration of the, I mean, concentration of water vapor in the atmosphere is more than the surface. So obviously it would come diffuse from the air to water. So net negative direction indicates that the diffusion takes place from the air to the water surface. So that's the direction of diffusion. Okay, this is the way to solve this problem.